In recent years, the rise of large language models has shifted much of natural language processing toward decoder-only architectures. But despite this trend, encoder-only transformers remain foundational to practical NLP. They power classification tasks, sequence labeling, span-based prediction, and are central to modern retrieval-augmented generation pipelines, where they serve as the backbone of both retrievers and embedding models. What makes them especially valuable? Efficiency. Encoders are typically more compute and memory efficient than autoregressive LLMs, making them ideal for high-throughput, low-latency applications. And while multilingual models like MBERT and XLM-R enable cross-lingual transfer, they face a fundamental trade-off: capacity versus coverage. Because parameters and vocabularies are shared across hundreds of languages, low-resource languages like Latvian often suffer from diluted training signals. Their representation quality can be compromised by imbalanced pretraining data, where high-resource languages dominate the training mix. This leads to suboptimal performance for languages with limited digital presence. Monolingual pretraining offers a compelling alternative. By focusing exclusively on a single language, we can optimize tokenization, leverage larger volumes of domain-specific text, and achieve stronger downstream performance, especially when sufficient unlabeled data is available. And yet for Latvian, such models remain scarce. This brings us to our work, the first comprehensive suite of monolingual Latvian encoder models, trained from scratch using modern architectures: RoBERTa, and ModernBERT, complete with long context variants up to 8,192 tokens. We trained them on a massive, carefully curated 6.43 billion word Latvian corpus, then evaluated them across a diverse benchmark suite spanning lightweight diagnostics, syntactic parsing, and semantic understanding. Our goal: to push the boundaries of what's possible for Latvian NLP, while demonstrating that monolingual pretraining can outperform even large multilingual models. So how did we build this system? First, the data. We combined large-scale web crawls, fine Web 2 and HPLTV2, with curated resources like the Latvian National Corpus Collection, news archives, academic texts, scan books, and fresh social media data. We also added a new Wikipedia dump and crawled tweets. The result: a balanced, high-quality mixture of formal and informal Latvian, covering modern usage, domain diversity, and linguistic richness. But quality matters more than volume. So we applied a multi-stage filtering pipeline: exact duplicate removal via metadata and text matching, near duplicate detection using min-hash LSH with 5-gram similarity threshold of 0.7, and language modeling-based filtering using a 5-gram KNLM model trained on the balanced corpus of modern Latvian. Documents with high perplexity, those that are noisy, non-fluent, or weakly Latvian, were discarded. To support long-context modeling, we further curated a specialized dataset: 1 billion tokens from documents greater or equal to 4,096 tokens, 1 billion from 1,024,4,096 token texts, and 500 million from shorter documents. This ensures robust performance not just on short inputs, but on complex extended reasoning tasks. For tokenization, we use the HPLTV2 Latvian tokenizer, a GPT-2-style byte-level wordpiece model with a vocabulary of 32,768. Initial experiments showed no benefit from increasing the vocabulary size, so we kept it lean and efficient. Now the models themselves. We trained 3 architectures under identical recipes: 100 billion tokens, effective batch size of 4.2 million tokens, using distributed data parallel on a single DGX machine with 8 NVIDIA 141GB GPUs. RoBERTa followed the standard Hugging Face recipe with 30% span-based masking. lv-deberta v3, trained using the RTD replace token detection objective with a 20% masking probability and a generator hidden size of 256. ModernBERT adopted a 3-stage training process: stability phase 70B tokens, context extension 20B tokens at 8,096 sequence length, and cooldown 10B tokens with a decayed learning rate. It leverages FlashAttention2 ModernBERT positional embeddings and token-level unpadding, achieving roughly twice the training speed of baseline models. All models were evaluated across 3 regimes: lightweight diagnostics, universal dependencies parsing, and a newly constructed Latvian word sense disambiguation (WSD) benchmark. Let's start with the diagnostics: Euro-eval-style tasks designed for quick screening with minimal fine-tuning. On Twitter sentiment classification, LTEC, our lv-deberta-base model outperforms all others, including larger multilingual baselines. It achieves a Matthews correlation coefficient of 54.2, surpassing even XLM-RoBERTa-large, despite having only 111 million parameters, compared to 560 million. On linguistic acceptability, SCA-LA, where models must judge whether a sentence is grammatically correct, lv-deberta-base again leads with 64.2 MCC, significantly above prior models. For named entity recognition, FSNER, the top systems converge near 89 micro F1, excluding MISC, suggesting performance saturation. Still, lv-deberta-base reaches 89, the highest score. On reading comprehension, WikiQA, the largest models, XLM-RoBERTa-large and lv-deberta-large, take the lead, but lv-deberta-base still ranks third with 69.2 F1, showing strong reasoning capability. But the real standout is common sense reasoning, COPA. Here, most models struggle. Multilingual and prior Latvian encoders average MCC below 20. But lv-deberta-base achieves 52.5, a massive leap. It's the only encoder to significantly outperform all baselines, indicating a truly stronger grasp of causal reasoning. And when we compare to large language models, GPT-5 dominates COPA, nearly perfect performance, but underperforms on other tasks, even with few-shot prompting. This shows that while LLMs excel in open-ended reasoning, specialized encoders still lead in targeted, structured NLP tasks. Now let's move to universal dependencies, a gold standard benchmark for morphosyntactic modeling. We fine-tuned all models on part-of-speech tagging, lemmatization, morphological feature tagging, and dependency parsing. On token-level tagging, UPOS, XPOS, UFEATS, performance is already near saturation. Top models exceed 98% accuracy. But parsing metrics, LAS, CLAS, MLAS, reveal deeper differences. Here, lv-deberta-base leads with 95.1 LAS, outperforming both multilingual models and prior Latvian-specific encoders. This suggests that monolingual pretraining provides a crucial advantage for modeling syntactic structure, beyond mere token classification. Finally, we introduce a new WSD benchmark, manually annotated from the Latvian WordNet. It contains 54,364 labeled instances across 1,821 lemmas and 5,459 senses. We cast WSD as a context gloss matching task, evaluating how well models align sentence contexts with semantic definitions. On this task, lv-deberta-base achieves 83.6% context, sense matching accuracy, and 78.9% top one sense selection accuracy, the highest scores across the board. Even the largest multilingual models fall behind, underscoring the value of language-specific pretraining for semantic understanding. So what's the takeaway? lv-deberta-base, just 111 million parameters, outperforms larger multilingual models like XLM-RoBERTa-large, 560M, and mdeberta-v3-base, 278M, while matching or exceeding prior Latvian-specific models. It leads across diagnostics, parsing, and semantics, especially in reasoning and sense disambiguation. But it's not just about performance. Our ModernBERT-based models offer a compelling alternative. High throughput, long context support up to 8,192 tokens, and faster training, thanks to FlashAttention2 and efficient packing. They're ideal for real-world applications, where speed and context length matter. And yes, long context variants match their short context counterparts in performance, with notable gains on extractive QA, where understanding extended passages is key. This work confirms a critical insight. For low-resource languages like Latvian, monolingual pretraining delivers superior results, not just in quantity, but in quality. It enables better tokenization, stronger semantic representations, and deeper syntactic understanding. We've released all models, RoBERTa, v3, ModernBERT variants, along with a full evaluation suite, benchmark datasets, and training code. These resources are available on Hugging Face and GitHub to support reproducible research and practical deployment. That said, we're honest about the limitations. All models are trained on Latvian-only data, so they don't generalize well to code switching or multilingual settings. The corpus is skewed toward formal written language. Conversational speech, dialects, and minority varieties are underrepresented. And while we filtered for quality, some noise and duplication remain. Our evaluation focused on supervised NLU tasks. We didn't measure retrieval quality, robustness under domain shift, or performance on specialized domains. But we've laid the foundation. Now it's up to the community to build on it. In closing, this isn't just about Latvian. It's a blueprint for how to advance NLP in under-resourced languages. By combining careful corpus construction, modern architectural choices, and unified evaluation, we can close the gap, not just for Latvian, but for hundreds of languages left behind. If you're working on NLP in a low-resource language, this is your starting point. Thank you for watching. Stay curious. Stay building.